Example 3 says, below is a graph of a function f of x. Evaluate f of 6 and find the limit as x approaches 6 of f of x. Let's do this first part where it's asking us to evaluate f of 6. So here is our x-axis and here is our f of x axis. The way that we would evaluate f of 6 is we would want to find 6 on our x-axis and then check where it is going on our graph. Notice though that there is an open circle at this point, and they've even labeled it for us at 6, 4. That means that there's a hole there and our function is not defined when x is equal to 6 because there's an open circle there. So we would say that f of 6 is undefined. Now we want to calculate our limit. So even though our function is undefined at x equals 6, there still is a limit. Now I'm going to show you when I was taking calculus in high school, the way that my calculus teacher taught us how to think about limits on a graph is by drawing a picture. So she told us that, there'd be a little kid standing on the x-axis and they were holding a balloon. And the balloon is going wherever the function's graph is going. So this little kid is approaching 6 on the x-axis. So I'm drawing the balloon, and they're getting closer and closer and closer to x equals 6. And so, here's my very poorly drawn balloons. And so the way that my calculus teacher in high school described limits to us from a graphical perspective is that there's this kid approaching the x value that you're looking at. In this case, it's 6. And you're trying to figure out where is the balloon going or where is the balloon approaching. And you kind of have to look at it from both sides. So here's the kid on this side of x equals 6, 2, and here's their balloon. And they're getting closer and closer to x equals 6. So you're basically asking yourself, where is the balloon heading? And in this case, if you said 4, you would be correct because the balloon is heading to this location right here, and the y value at that location is 4. So we would say that the limit as x approaches 6 of this function f of x is equal to 4. So we weren't able to just plug in 6 into the function because it was undefined here, but we were still able to calculate the limit because the balloon is getting very, 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 very close to the value 4. And so if we made a table like in Excel or something, it would probably look something like this. As you got really close to 6, if you plugged in like 5.999, then the y value might be like 3.999 or something like that. And then if you plugged in 5.9999, then it would look like 3.99999 or something like that. And same thing from the other side. If you plugged in a number like 6.0001, then you might get like 4.001 or something like that. And these are just estimates, but at the end of the day, the limit is equal to 4. Let's talk about one-sided limits. In the previous example that I was showing you with the drawing and the little kid with the balloon, I said that we had to take a look from both directions. If they were coming from the left-hand side and from the right-hand side, we had to kind of observe both of those. Well, it turns out we can evaluate limits from a single side instead of coming in from both sides of the x-axis. So the limit from the right is denoted with this notation, and the main difference is there's a little plus sign superscript on the c, and so this notation tells us that the value of f of x approaches the value L as x approaches c, but x is greater than c. That's the important part here. So it's approaching it from the right-hand side. So for example, if we were calculating the limit as x approached 4 from the right-hand side of that previous function, then we'd want to observe x values like 4.001 and 4.0001. So we'd want to come in from the right-hand side where our x values are larger than 4. The limit from the left, here you have a little negative sign as the superscript, is the same thing, means that the values of f of x approach the value m as x approaches c, but the x values are less than c. So for this one, again, if we were doing that previous example, then the x values we'd want to look at are 3.9999, like that, the values that are smaller than 4, but getting close to 4 from the left-hand side. Example 4 says, use the graph of the function f of x to answer each question. Use infinity, negative infinity, or DNE, which stands for does not exist, where appropriate. So the part A wants us to evaluate f of 0. So if we find 0 on our x-axis and we go upwards, there is an open circle here. That means that our function is undefined at x equals 0. Now it wants us to evaluate f of 2. So we'd find 2 on the x-axis, and the graph is going through this ordered pair right here. Hopefully you recognize that the ordered pair is 2, 0, which means that f of 2 is equal to 0. Okay, so let's do 3 now. We want to evaluate f of 3, so we'd find 3 on the x-axis, and then go up, and there's an open circle, so it's going to pass through, and our graph is right there at that point. That point is 3, 3, which means that f of 3 is equal to 3. Okay, so now we want to compute some limits. The first limit we want to look at is the limit as x approaches 0 from the left-hand side of f of x. So here's 0, and we want to come in from the left-hand side. So here's the little kid. Now, this is where the balloon thing kind of is faulty, because if the balloon is following the graph, it kind of appears that the balloon is underground, but whatever. Maybe if it's underground, you can kind of think of it like a yo-yo or something. So there's the first iteration, and then the kid is getting closer to the x value 0 from the left-hand side, and their yo-yo. And you can't see the graph, but the graph continues on forever in this direction. So maybe let me draw this. It's going to look something like that. So our yo-yo is down here. So how do we denote that as far as computing the limit? Well, it turns out that the limit does not exist because it's not approaching some finite number. However, it's a special kind of does not exist in that the yo-yo is going down maybe to the depths of hell forever. So the limit here is, you'd technically be correct if you put does not exist, but we want to be more specific than that, and it's actually going down to negative infinity. Okay, so in order for the limit to exist, it has to approach the same value from the left-hand side and from the right-hand side. And so notice that, because here we're asked to find the limit as x approaches 0 of the function. So if I drew my little person here, my little kid with their balloon, if this said from the right, then the value would be 2 because it's getting closer and closer. The y value is getting closer and closer to 2. However, it's asking for just 0 overall. And because the left-handed limit and the right side limit are not the same value, this is a does not exist scenario. Because again, the right-handed limit and the left-handed limit are not the same value. So that's just a flat out does not exist. Okay, so now we want to look at the function. We want to find the limit as x approaches 3 from the right. So here's x equals 3, so I'm going to draw my little kid with the balloon. And as the kid is getting closer and closer to 3 from the right, what is it approaching? Well, the balloon is going right here, and the y value for this point is 2. So this is going to be 2 there. Now, it wants the limit for as x approaches 3 overall. So if I did the left-hand limit, it's kind of small, but I'm drawing this kid. The left-handed limit, or the left side limit, is approaching 1, but the right side limit is approaching 2. So because those are not the same values, the right-handed limit and the left-handed limit are not the same, we say that this does not exist. Okay. Part H is kind of a preview into a future section, but we can still work on it. We're finding the limit as x approaches negative infinity. That just means like if the kid with the balloon continues to walk left on the x-axis forever, where is the balloon going? So here's the kid, and they're just walking left forever. So where is the balloon going? And hopefully you recognize this dashed line here indicates that there is a horizontal asymptote, and the balloon is getting closer and closer and closer to that horizontal asymptote, which that value there is 1. So that limit is going to be 1.